Oh, hello everybody. Great talk, Peter. Hopefully you can all see me okay. My internet quality isn't the best, so I will mute my video for this talk.
You're good so far.
Awesome. Well, thanks all for being here. My name is Bryan Stearns, and I'm a PhD student with John Laird. And my research focuses on what kind of human modeling can we do with Soar. And I'm going to be talking today about a cognitive model that we've been working on of human learning and transfer with Soar. So let's say you have 3 different tasks that humans do of a wide variety between them. You have, say, a text editor's task, like you're typing stuff into Emacs or a word processor. You have a mental arithmetic task where you're just doing some number crunching in your head. And then you have a Stroop task, which is a common experiment in psychology where you have some text shown on a screen where the text might be one color, but the actual color of the font might be something different than what the text says. And you have to try to say what the color is. And you want to make a single Soar model that can do all of these tasks. It is task general, and it's able to do all 3 of these of the wide variety. But you also want it to match human learning and transfer profiles. You want it to be able to do the things that humans do, have the same kind of learning curve, and offer a potential explanation for how it is that human cognition does what it does. I will be going through these 3 tasks for this talk because the goal is make a model of these 3 tasks specifically for this example. So I'll explain each of these tasks in a little bit more detail before diving into how you might model these. So editor's task, this was an experiment done in the 80s where you take some human typists that have never used a computer text editor before, and you give them some written edit instructions on a piece of paper that say, take the text and do these edits, add a line here, remove a line there. And then you set these people in front of some unfamiliar text editors they've never used before on a computer. It's like Emacs or EDT or something else. And then you measure how long it takes them to do various tasks. So you don't need to know the details of how this experiment worked, but the main thing to take away from the graph here you can see is that humans start out taking a long time, say like 120 seconds per edit operation, and then over time they get faster and faster. That's a classic learning curve. The dotted lines show where they switched to using a different text editor, but humans were able to transfer between text editors so that the learning curve continued even when they switched. So that's the editor's task. We also want to look at the arithmetic task. In this case, it's a bit simpler. Humans just memorize a certain algorithm with various inputs, and then they're just given repeatedly different inputs to crunch the algorithm on. And in the figure, the main thing to notice is like the first 50 trials with the memorized algorithm, there's a classic learning curve, power law of learning. They get faster with practice. On the right are different transfer cases that humans were sent to do using different algorithms. The data points are averaged as reported in the Ilios 1986 paper. But the main thing to look at is this simpler learning curve that the time scale is only like around 10 seconds per operation compared to the 100 seconds of the editor's task. And then there's the Stroop task, which I explained before. You're supposed to say the color and not the word that's written in the text. And a well-established effect when humans do this is that it takes us longer to answer when the text and the color mismatch. And we can describe working memory interference as the difference in how long it takes us to respond between when these mismatch and when they match. And the Chain and Morrison study in 2010 showed that you can reduce this interference by practicing a working memory span training task where you're trying to remember a long series of digits or letters. And surprisingly, that would actually provide significant reduction in interference for those who had taken that training compared to those who didn't. So these are our 3 tasks: the editors, the arithmetic, and the Stroop task. And we want to make a model that can do all of these, just a single model in Soar. Now, there is actually a model that has been published already in cognitive architecture research, Actransfer, that can do all 3 of these tasks. It is based off of the Actar architecture, and it works by receiving declarative instructions about what the task is, similar to Rosie, like we've been hearing about so far. And then it practices using a general set of production rules, those instructions, and it compiles faster and faster decisions and rules over time with practice. And it also composes its rule knowledge in a specific way that allows significant transfer, the same kind of transfer profiles that you see in humans. So here you can see on the right, the Actransfer agent results for modeling the editor's task. The time scaling isn't quite the same for the first couple of days, but the transfer trends are the same, which was a significant result. So given that this model already exists, let's investigate how exactly it works and what this might imply for doing things in Soar, and if there are things that need to be improved perhaps to make a true general model of human learning. There's always future work. But if we look into how Actransfer works, we'll notice that its results rely heavily on this particular formula, which comes from Actar theory, the formula that calculates how much time comes from retrieving something from long-term declarative memory, what we would call SMEM in Soar. And in this formula, there's two factors. Mainly, there's the activation of the retrieved memory. The higher the activation, the faster it's modeled as being retrieved. But then there's also this F sub R latency scaling factor, which is a parameter that you enter into the agent that's task specific. So if you look at the behavior of the Actransfer agent, you will notice that if you remove the amount of time that was contributed by using this formula for declarative retrievals, the profile of its behavior flattens significantly, down to the order of about 20 seconds per operation instead of the 80 to 100 seconds. You look at the Stroop model, you'll notice that its results also come from using this same formula, where the amount of time it takes for a person to respond depends on how much time is modeled to retrieve the answer, which is based on the activation of that answer. And the activation itself depends on whether there is congruent or mismatching stimuli coming in. So once again, we're using the same formula to drive the results of this answer. And you can see on the right here is the Actransfer agent's results. It does achieve similar behavior and learning as the humans. But again, it also relies on this formula, which is interesting. And you look at comparison with the arithmetic agent, you notice that the F sub R scaling factor can vary by an order of magnitude between the two models here. For the editor's task, FR was 1.5, but for the arithmetic task, the scaling of the whole task is an order of magnitude less. Also, we're at 10 seconds instead of 100 seconds. And you'll notice that this agent also, well, it gets decent human results, but again, they're dependent on this formula. So this makes us wonder, something might be missing here. If so much of the behavior is dependent on this number that gets calculated separately from the literal computation of the cognitive model. It's something that's based on more under the hood metadata. Maybe there's a way we can model this more explicitly in Soar. Maybe. Can we do better and avoid the need for a task-specific scaling parameter? Avoid the need to change F sub R for each individual task, so we truly have a task general model? And the answer is yes. This is what I'm talking about here in this talk, model that we've been working on here called the primitive operators model. I'm talking here about version 3, which is published in Cognitive Science this year. But it uses Soar PSCM theory to explain why the different tasks are different, so that you're not depending on these different values of a F sub R parameter to explain why different tasks take different lengths. So what is Soar PSCM theory? John talked about it at the beginning of the day. Problem space computational model, where you break up a task into this hierarchical description. For example, I use a simple transcribed text task where you're just taking text from a prompt and you're typing it into some computer editor. So the transcribed text task itself, you can break that up into two operations of get text or write text. Get text itself can be broken up into the operations of finding a prompt, reading the prompt. Writing the text can be broken up into tasks of placing a cursor or typing a word. And in Soar, we would treat these as a hierarchy of goals and subgoals, where each triangle here represents a problem space. And in each problem space, you have a set of operators that are of operators that are available to you in that space to achieve your goal. Now, what does this imply? This long-standing Soar theory of problem spaces, well, it takes work, it takes effort by the agent to go from one problem space to another. It takes a decision cycle to go from a goal to a sub-goal. This would imply that if you're in a task that has a deeper hierarchy of problem spaces, then it's going to take you more time. It's going to take more time for your agent to navigate this hierarchy and complete its task. And if you look at the actual agents used for the Actransfer work, you'll notice that those tasks do differ by the depth of their hierarchy. For the goal stack, the editor's task is fairly complex and deep. You have operations like edit line, which requires finding a prompt or reading a prompt, and so on. For example, I believe that actual task hierarchy goes down to like a depth of 6 different goals in a stack. Whereas the arithmetic agents is pretty shallow. You only go to like a depth of 2, where your step 1 is add a plus b. Go back and step 2 is subtract b from c, and so on. It's fairly simple. So just from looking at the problem space hierarchy, you would predict that the arithmetic agent should be a lot faster than the editor's agent. And so this is what we model in Prop 3. We explicitly represent the problem space as a declarative structure that gets retrieved from SMEM into working memory. This structure, we call a procedure context in Soar. It's a declarative structure in working memory that just describes what operators are available in the current problem space. And then a general set of production rules in the Prop 3 agent interpret the instructions that are written in that declarative procedure context structure and propose whatever that procedure context says to propose in that problem space, and apply whatever the instructions say to apply in that problem space. This means that you can have a task general agent that can do any problem space as long as it's instructed by this procedure context structure that's retrieved into working memory. And none of the problem space is baked into the agent production rules. So this is our first big nugget about this model. You have a small set of productions that work for all proposal and applications rules. It's general to whatever the architecture is capable of. And now, how does this affect timing? Soar timing, as has been mentioned in previous talks, we usually do 50 milliseconds per decision cycle. And I mentioned before, it takes 1 cycle to enter a sub-goal in Soar when you have an impasse. And it also takes 2 cycles to retrieve something from SMEM, a cycle to send a query to SMEM, and then another cycle to actually collect the result off of the SMEM link in working memory. So using this model of retrieving this procedure context description of a problem space from SMEM into working memory, that would take 150 milliseconds per change, 1 to enter the substate and 2 to actually query the result. And you do this every time you enter a substate. So we predict the more subgoals per task, the longer the predicted time. And we test this using the same Actransfer agent designs that I've already been showing you their results from. We'll import the same agent task instructions that they used and use the same goal changes. But now every time we change a goal, that adds our 150 milliseconds, which were not represented in the Actransfer agent. All right, and we look at our results. And using this method, we actually get about the same performance as the original Actransfer agents got, except for we're not using any kind of extra formula to simulate the timing for each task scale. For the editor's agent, we get that same 80-second scale. For the arithmetic agent, we get that same 10-second scale. For the arithmetic agent, we actually even get an improved model of the learning curve compared to what Actransfer had. So this is significant and kind of unexpected and cool that this happened to work just by making this change of how you treat problem spaces. So this is our second big nugget. You can get task general timing approach for modeling human learning just by using Soar's natural problem space theory. Now the Stroop model, I didn't mention yet how this works in Prop 3, but since we're not using that retrieval formula from ACTAR, the way that this is modeled is also different, but it's still based on problem spaces. Because using problem spaces, whether you respond with the word yellow or the word green based on what you see on the screen is going to depend on which problem space you have entered as an agent. You could choose to enter the say text problem space, and then you say what's written yellow. Or if you are prepared to answer green, you can enter in a maybe harder to access problem space that's not your default preference to actually say the color. And if you've trained to your working memory skills, you trained yourself to prepare to enter the say color problem space as soon as you need to. And using this approach to modeling working memory interference with problems and spaces, we also get a model that matches the human results for this task. Both the Actransfer and the Prop 3 model are slightly different from the original human results, but they both have the same trends, which is interesting. And there's future work also to explore this particular type of research. But there's our third nugget, that you can use problem spaces in Soar theory to also model working memory interference.
3 minutes.
So summary, yeah, I'm running low on time. But we have an improved model of human learning using a small set of productions for all operators. It's a task general agent, and we have a task general timing method using Soar problem spaces. And the function T-retrieve, as used in Actar, has a long-standing solid history of use in cognitive modeling. I'm not trying to say that that's not appropriate, but more research is required to figure out exactly how to best use that formula, or what all the implications of this kind of result mean as far as that formula is concerned. And there's also more experimentation to do with just trying more tasks and seeing how far that this idea can be used. But that is my talk. Be open for questions now. Thank you very much.
Well, someone correct me if I'm wrong. I don't see any questions in the chat, but I have one, Brian, and I know about the system, so I get to be mean and ask a tough question. You were sort of alluding to this notion that that your measure of time is sort of more real in a sense. It's the computation the system's actually performing. But how long does Soar actually take to do any of this? And do you think that you have a good reason to have assigned the timings that you've assigned for what Soar is doing?
Well, that's a good question. So as far as running this agent in practice, when I click play, as it were, on my Soar agent, it runs anywhere from like 6 to 40 times real time. The allocation of 50 milliseconds per decision cycle, different people have used different numbers for that in source history, but the standard in recent history has been using 50 milliseconds per decision cycle, which is also what Actar uses by default. And that is also the same as an Actransfer. So for that, I am simply citing the previous research using cognitive architectures that has pretty solidly landed on this number so far. These agents also do add time for doing like motor actions in the world, which is separate and which I didn't talk about here. But for that, I also just copied from what Actransfer did in their model so that everything would be comparable.
All right, one more question before your next talk. Do you think you could use this method along with maybe protocol analysis to account for individual differences in the timing of task performance? So looking at individuals performing this task. This is from Bob Ray.
This is an excellent question. This is something I have thought about. In this method of representing tasks with this network of problem spaces, an individual difference, the biggest factor for individual differences in my mind would be different hierarchies as represented in SMEM. A different individual can have a different structure of links in SMEM, and those could even change in one-shot learning as they get better at the task and understand the task better. So that would be something worth exploring in the future, is how does declarative learning factor into then defining your problem space hierarchy?
All right, that's all the time we have. In fact, I'm eating into your second talk a little. Would you please proceed?